My name's Bart Maple with BMWC. This is my colleague Steve Klein. We'll quickly go over the agenda and then do some introductions, a little bit about ourselves. But we'll talk to you guys about the fab design, the actual facilities. We're going to talk a little bit about clean room design, the utilities that feed these facilities, our role in that world at BMWC, and then kind of how these construction projects differ from other types of construction. And then we'll talk a little bit about some of the career paths that might be of interest to you guys. Can you guys hear me okay? All good? So like I said, my name's Bart Maple. I'm our Chief Operating Officer at BMWC. Graduated here at Purdue back in '98. You guys weren't around then, obviously. In the construction engineering program, which is now part of the civil engineering program. Started as an intern and have never left. Worked for BMWC my whole career. Went out to Seattle for about 8 years and worked in our industries out there. And then I went to Houston and worked down there for about 7 years. And then now I'm back in Indianapolis, is where our headquarters are. You want to do a quick intro for you?
Yeah, I'm Steve Klein. I'm our business development manager for our Western region. I service a lot of our semiconductor clients which end up being in that region, the Intels, TSMCs. We have about 35 semiconductor customers, in that region. And been doing this, graduated Purdue 2008 with building construction management back then, a little bit closer than Bart, but yeah. And moved out to Seattle, then moved to Portland, and I've been in Portland, Oregon region ever since. Traveled between Seattle, Portland, and Phoenix, Arizona, where predominantly all of our semi clients are.
So this is 10 years of gray in the industry, right?
Yeah.
Just real quick, a little bit about BMWC. So we're headquartered in Indianapolis. It stands for Baker, McHenry, and Welch, the three founders of the company. We're in Indiana, Chicagoland. We've got an office up in that area. We're in Ohio, in North Carolina. And then out on the West Coast, we're primarily in Oregon and Arizona. And that's where the vast majority of the chip manufacturing facilities that we work for are in Oregon and Arizona. So what happened was, back in the late 90s, we did primarily pharmaceutical construction and oil and gas construction and power construction, power industry. And we wanted to diversify. So we bought a company out in the Seattle area called Pilchuck Mechanical, and they had a customer called Mashishita, which is a gentleman's last name, who actually, that company now is Panasonic. He was the founder of the company that they now call Panasonic. I'm sure everyone's heard of Panasonic. Well, about a year after we moved out there, Mashishita decided to withdraw from the U.S. This was their only U.S. plant, and move everything back to Japan where they were headquartered. And so we had a brand new office and a brand new company out on the West Coast solely to chase semiconductor work, which was no longer there. So we kind of had to pivot. We went back kind of to our roots of what we did, but also we started to expand down to Portland at that time. And this is all the companies that are in this kind of ecosphere of semiconductor construction, or semiconductor manufacturing, I should say. And so we started an office in Portland in '99, shortly after moving out there, to chase the customers like Intel and others that Steve will talk about. So that's kind of our history into semiconductor construction.
Yeah, this is Silicon Forest. This was a flyer. We actually have this hanging in our Portland office, but kind of the bottom here is Eugene, Oregon, where University of Oregon is, all the way up to kind of up into Vancouver, Canada. And these are all the companies that are associated with that kind of the semiconductor tech industry up there.
So I'm going to pass it off to Steve here now.
Yeah.
The down arrow and the pointer.
Okay, so we were kind of asked to talk a little bit about the construction of semiconductor factories, what that looks like, how the factories are built, why they're built the way they are. So this is what we're looking at right now is kind of a cut of a semiconductor fab from top to bottom. So, well, first off, I should say, my wife told me I needed to start with a joke. So, do you guys like jokes? So why is a semiconductor fab a terrible place to have a party? Anybody? Because they're worried about clean rooms. Okay, all right. Okay.
Not one laugh, except for the
Professor, that's fine.
I have kids, my sense of humor is terrible.
So the whole concept of a semiconductor fab is to process or manufacture semiconductor wafers, which requires clean space to do that. When we talk about clean space, we're talking about particles in the air. Like this kind of dripping light here would not be allowed in a semiconductor fab. That's a pretty extreme version of it, but I'll talk about it in a minute. But there are different levels or classes, and those classes are designated by ISO classes. ISO is a global standards organization about how many particles you're allowed to have per whatever section of air that you're looking at. So to do that, again, we're looking at a kind of a cut of the building. Where I'm going to start at the bottom. So what we have first is a fan deck, and the fan deck is where we house the air handlers and heating and cooling equipment that actually flows the air into the building, and it pulls filtered air from outside and pushes it down through what we call an interstitial. And all an interstitial is a shallow duct or plenum, we call it, where air flows through and it flows down through what they're calling here a UPL ceiling, or what we call HEPA filters. So like if you look at the ceiling right now, or a lot of classrooms, you'll see a 2x4 panel. That 2x4 panel in a clean room would be an actual filter where air pushes down from above the ceiling through the filter into the room. So that filter is filtering out particles. And we just actually had a tour of the Burke Nanotechnology Center. Has anybody been to the Burke Center? Has anybody seen that? A couple people. If you have a chance, have a chance to go get a tour there. It's a very good example of what a clean room looks like. It's actually, we did some work, Bart mentioned Seattle, we did some work at the University of Washington, also has a similar clean room. It's a little bit less realistic, I would say, compared to what you all have here at Purdue. So I would encourage you all to go take a look at that. So we have the HEPA filters. The filters push down into what we would call the clean room, or the process level. That's where all your process tools live. A lot of the clean utilities live, but that's where the wafers are, where the magic's made, where the magic happens, where the wafers are made. And then the air flows downward, continues to flow downward through these little triangle, and you'll see them better in the next slide, are called pop-outs. So this is typically a thick concrete slab with round holes in it to allow utilities to pass through, pass up, and air to pass down. And it passes down into what we call a subfab. The subfab holds all of your main process equipment, vacuum pumps, chilled water pumps, piping, exhaust systems, electrical systems, and allows you to perform maintenance on all those systems as well. And then from there, the air flows back around through these building plenums and back up and recirculates through the clean room. So that's kind of a high-level view of what that looks like. There are other levels. HPM rooms, these are rooms that house monitoring equipment for dangerous chemicals and gases. There's utility levels for wastewater, large utility banks for electrical, things like that, as well as electrical rooms, maintenance shops, computer rooms, smocks, clean rooms, or gowning rooms, things like that to help support the system. Any questions? If you have questions, anytime, feel free to raise your hand. I'm going the wrong way. So how we achieve that cleanliness is through something we call laminar flow. The filters help filter out the particles, but when we're walking into a room, we're actually creating particles. And it doesn't matter, you can see somebody wearing a gown suit right here. That helps to keep our particles from our body inside that suit and not contaminate the air around us. But the laminar flow from top to bottom, and there's two different types, I call it two different types of kind of clean room flows here that you're looking at. These are the pop-outs that we showed earlier. They're standing on what we call an RMF, or raised metal floor. That allows another level of air movement below the floor. So the air would come from the filters, through the process room, through the floor, and through the pop-outs. What we have here is actually, you can tell it's a concrete floor. So the air passes from the filters through the process room and then through air return ducts in the bottom of the wall on each side of the clean room. So again, kind of keeps that flow moving. and that's what keeps particles, kind of keeps particles moving in that same direction. Any kind of turbulence, moving around, any of that kind of things, equipment moving, belts moving, any kind of materials you would bring into the clean room would cause contamination of that. So it's all pretty heavily monitored. This is what I was talking about with the ISO clean room standards, and we were talking a little bit about this at Burke earlier. So when I talk about particle counts, this guy right here is actually measuring particle counts coming out of a specific filter, and this is how clean rooms are certified. A typical clean room for semiconductor fab is going to be around ISO 4 or class 10 is what a different way to pronounce it or to say it. Class 10 is 10 particles less than half a nanometer
Per cubic meter.
per cubic meter. Yeah. So we're talking pretty low levels. What Burke actually has a couple of rooms that are ISO 3, which is 1 particle less than half a nanometer. So it's hard when you look at or try to think about the concepts of these. It's a little bit hard to visualize. What did we say a human hair was?
He just told us.
10,
Is it 10 nanometers?
10 nanometers,
Right, for a human
something
hair?
like that. Yeah. So just for perspective.
No, it's 100. It's 100 nanometers. So it's,
You're right. It's 100.
yeah.
Okay. So now we can talk a little bit about the different types of clean room and clean room designs, right? There's several different ways that you can design a clean room. I apologize for the blurry. This is kind of the nature of semiconductor fabs. They're all very secretive, right? Everybody kind of wants to keep their intellectual property to themselves, so it's hard to find photos of what we do in these places. So the first one I'm going to talk about is called a ballroom, and it's exactly what you would think. Big wide open room. You can see all the lights and filters up above. You can see the perforated floor down below. All the air comes from up above, flows down, and then gets recirculated like you see it. What you see here is all the process tools. Now these are the tools that are actually making the wafers, and they're staged in this type of a clean room, typically staged like an assembly line, like you would think of. A wafer would start on one end of the fab or the ballroom, and it would end on the other end of the ballroom, and then it would go to packaging from there. Now the things that the positives of this type of design is it allows for a lot of modularity. So when we talk about having to change out tools, say we're building 500 wafers of one chip, we get done with those 500 wafers, we have another customer that comes in, wants us to build 500 of a different type of wafer. So you're going to take those tools that you were doing, you may need to move some around. This allows for easy move in and move out. You can see there's wide aisleways. This isn't always the case, I assure you, but there's wide aisleways to get tools in and out. These are 2x2 perforated floor tiles. Each one of those tiles you can pull up, and there's typically about a 2-foot subfloor, or below RMF is what we call it, where a lot of utilities are ran, and it allows you to get different processes to those tools without disturbing other parts of the clean room. The next one I'll talk about is the bay and chase, and this is somewhat of an older design. It's actually what Burke has. They have a little bit of both of the ballroom and bay and chase. But what the bay and chase kind of allows you to do is take a process tool, and this is the bay here, and this is where the actual workers that are operating the equipment work. The tools, the front of the tools and the interfaces, the computers that they use are facing through the wall, so you can operate with them. And all the maintenance equipment and all the kind of the working end of the tool is all behind a wall in a less clean space. So we're probably talking like an ISO 5 or an ISO 6 back here. Whereas this part of the clean room is kept in that ISO 4, ISO 3 level. So it allows you to go and maintain this equipment, maybe move equipment in and out a little bit easier without disturbing the clean environment in the actual process spaces. And you can see the pop-outs a little bit better here too. And kind of the last thing I just wanted to touch on are microenvironments. A lot of tools in themselves, and I forget his name, at Burke. What was the guy that was giving us the tour?
Yes.
Anyway, he was talking about a vacuum, a dual chamber tool with a vacuum that flowed through both sides of the tool. So what that allows you to do is create a microenvironment or a vacuum. So anytime you expose a wafer to air, it's going to have some level of oxide that develops on the outside of it. When you keep it in a vacuum, that doesn't happen. So it allows you to take that wafer, process one side of the tool, move it to the other side of the tool without worrying about that. So along with a vacuum, you'll have microenvironments inside of these tools that have an ISO 3 or less environment inside of them to help prevent contamination between tool processes. So, grab a water. So now I'll kind of get into more about what we do as a company. Bart talked a little bit about this, but we are a process piping company. And when we talk about doing these, we're not actually building the structure of the building. We're not putting the filters in. We're not building the walls. We're feeding the utilities, the gases, the chemicals, the waters, the waste systems. All of that is what we would supply to the tool for it to be able to function. So we'll start with air separation plants. So when you talk about the gases that come, think about the air that's around us. Does anybody know how many gases are in the air? I don't. Nitrogen's the big one, right? There's some hydrogen, there's some oxygen. So what these plants do is actually pull air in, and I'll be specific because I've actually built one of these before. This big yellow thing here are filters, intake filters. So it filters the air going into a compressor, and this compressor, think of an air compressor in your garage, except for that compressor is the size of a small bus, compressing the air, feeding it into separation units that filter out the gaseous air, or the air as we know it. Then it gets fed into these towers, which are typically called the cold box, and these cold boxes have turbines inside of them that hypercompress the air and turn it into a liquid form.
Like negative 300 degrees Fahrenheit, super cold, and it actually turns the air to liquid.
Yep. And then from there, there's more of a distillation process. Think of like how they refine oil or how they make vodka, kind of things. Separates it into its different parts, and then feeds it either into a gaseous storage or a liquid storage. And these kinds of plants use both, different kinds, depending on what it is. A lot of it's gas. We saw today at Burke, they had some liquid nitrogen lines that get fed to different tools and different
Does that
equipment.
make sense? So that distillation takes liquid air and turns it into pure oxygen, pure nitrogen, pure hydrogen, pure argon, and sells those pure gases to industries all over the place. Hospitals use oxygen. Obviously, semiconductor fabs use a lot of specialty gases.
Yep. And you'll see these outside of a lot of different facilities. It's certainly not just in the semiconductor space. So, but you will typically see a large facility like a TSMC or an Intel or a Global Foundries, just some names that you guys were mentioning.
But this plant could be $200 to $500 million for a big fab.
Yep. Yeah, and the Intel facility that's outside of Portland has 5 of these towers just to feed one plant, or one campus, we'll say. So they're big and complex, but very interesting. Any questions on gases? Yeah. Good question. They actually do. Yeah. So this one, I don't know what, it's Syed, must be a Middle Eastern one, but Air Liquide, Praxair, Airgas, I don't know if you've ever heard of these companies. Linde.
If you Google tonight how air separation, it was invented by Linde. The guy
Yeah.
that invented it was named Linde, and that's one of the big companies that they invented this process. Linde did.
Yep.
But you're exactly right. All semiconductor fabs will subcontract or buy their gases from one of those companies, and they will actually build the plant and operate the plant.
And what you'll see is these plants are typically either outside of the campus or they may be a part of the campus, but they're actually managed and operated by those third-party companies. So the reason that great question. The reason that the company like Intel would buy this is to get a cheaper price or more availability on the gases.
So then, in terms of scale, you said you can have different sizes.
Mhm.
Would it, how do I say this? How often does someone need to, I guess, make this outsourcing to a company to manage it? Like, how big of a scale does it need to be for somebody to do this so they actually build a plant at their location rather than
Yeah.
get this up purchase and delivered?
So we were talking to the guys at Burke about this because they currently have a liquid nitrogen tank outside, similar to something like this, and they were talking about installing a nitrogen generation station, right?
So even at the campus here, they're talking about
Right.
making nitrogen, if you will, separating nitrogen and not buying bottles.
I've installed this scale. I've also installed some that are much smaller than this. So typically, it's the semiconductor company will look at what they think their needs are as far as volume, and they'll discuss with their vendor and talk about what makes most sense cost-wise to do it. And they have varying options. So
About 15 minutes.
okay. Here I was worried about it. These next couple will go quick. So again, talking about bulk chemical storage, kind of a similar process. A company would have a vendor that would provide the chemicals, anything that they need, hydrochloric acid, isopropyl alcohol, those types of things. The owner or the company, the semiconductor company, would look at what they need, look at how much storage they think they need, and then deal with a vendor who would provide these. There's less production on site of these types of chemicals. Obviously, a lot more hazardous, a lot harder to get. You can't just pull them out of the air or the water. But again, another big thing. It also comes with. Wanted to touch on this. Because these are mostly hazardous chemicals, sometimes explosive chemicals. There's gases like silane that are, if you expose silane to the air, it immediately ignites, explodes, basically. So a lot of obviously dangerous things there that are federally regulated by the Department of Homeland Security. So they have this RCRA tagging, and I forget what RCRA stands for, but basically it's regulations that they mandate that the company lets the government know how much of that chemical they have on site. And then we'll talk about bulk water reclaim. So think of a wastewater treatment plant in your hometown, right? So a lot of these companies have their own self-contained water reclaim and treatment, usually for either pre-treatment to send to the city as wastewater or to reclaim. These plants use a ton of water.
Millions of gallons a day.
Millions of gallons a day. So obviously, the more of that they can reclaim, the less that they have to purchase. So they'll build these types of facilities to help with that. And then again, kind of getting to more of what we do as a company: process piping versus mechanical piping. Think of mechanical piping as the air that heats and cools this building, right? That's more mechanical piping. Usually, that's done with some sort of either refrigerant or water process. We do some of that work, but when we're talking about semiconductor fabrication, we're talking about more support systems for chemicals and gases that support process equipment or manufacturing equipment is an easy way to think about it. And then you wanted to talk a little bit about waters.
Just real quick, ultra pure water is a huge piece of these facilities. So they use a lot of super clean water, right? We do a lot of work in the pharmaceutical industry that also uses water. They call it water for injection, where it's called ultra pure water in the fab space or the semiconductor space. And I just wanted to touch on real quick, both have similar construction, but in the semiconductor world, that water has to be super clean because of particulate matter and how they need the cleanliness for, I guess, the technical reasons. In the pharmaceutical world, the reason the water has to be so clean is because, and it needs to be clean for a different reason, it's biological. So you need that water to be clean so you can inject it in your body without causing issues. So it's more regulated by the governments, the European regulation and the FDA here, because you're going to inject that water into your body. That's why it's called water for injection. Whereas in the semiconductor world, it has nothing to do with anything other than they need that water super clean of particulates so that they can use it in their process. So similar construction, but different reasons and different regulations.
Right. So when we think about if anything that touches a wafer has to be super clean, and you think back to the pipes that the gas goes through to get to that wafer, that has to be clean before it even touches any kind of gases, right? So when we do our fabrication or installations, we're doing things in clean rooms. So these are both our clean rooms in our Portland fabrication shop. We have a ISO class 4 clean room that we use for stainless steel fabrication, ISO class 6 clean room that we use for plastics fabrication. So everything from, and when we get these products, they're actually in 2 bags. So a fitting that would make a 90, that'll come double bagged and cleaned from the manufacturer. We don't open it until we get into our clean room so that it never gets exposed to those types of atmospheres that would allow particles to contaminate anything.
It's the same elbow that you see in Home Depot. It's just
Yeah.
super, it's not the same same
Yep.
use to transfer water.
Basically. This is we were going to watch the plastic fusion process. We're running a little low on time, so I'll leave this to Professor to send out. But it just basically shows how these plastic pipes are welded. They're actually fused with heat, so that it's like welding a piece of metal pipe as opposed to like a PVC where you would use a liquid to do it. Anyway. And then a little bit about tool install. So once we get all these utilities to the fab, where do the tools come from? So there's 3 main steps here. One would be pedestal installation. So these tools, you think of these tools, some of the ASML came and talked, I think, last year or this year.
Not yet. You guys are the first, so feel free to spoil
Oh.
the presentation.
Oh, wow, okay. So ASML is they're a Dutch company that makes lithography tools. And they make the only, I think they call it extreme ultra lithography or something. EUV is what they call them. So they're the only ones in the world that make these tools. These tools are the size of a school bus. So when you think about trying to put those tools inside of this environment, it's pretty it's interesting to have to figure out how to engineer those systems. So obviously they need some sort of support system. Think of that as a pedestal. So that the tool would sit on this pedestal. And then once you have the pedestal installed, you're going to do a tool move-in. So you're going to actually take that tool, move it in one piece or several pieces. And there's several ways to do that. But think of moving a vending machine or something into a building. And then you have the tool hookup, which is where we actually take the utilities that we've brought up to the subfab. It's underneath the floor here, and hooking them onto the tool. Once that happens, there's a lot of qualifications and other things that happen from the tool vendor to get it started. And then Bart's going to talk a little bit about the life of a construction project and what that looks like.
Yeah, so we'll speed it up a little bit.
Yeah.
Running short on time, I want to leave time for questions. But I wanted to mention, like the big tools that he was talking about from ASML, those might be $200, $300 million a piece. I mean, the price of these tools it's just gone through the roof, and it's really astronomical. Quickly talking about the life of a construction project. You identify the project, then you do conceptual design. So you're doing, does this make sense? How big does the facility need to be? What utilities are going to be needed? Understanding what the throughput is going to be. What's the chip output? Does it make sense financially to build this facility? Once that gets green light, then you go into detailed design. So that's when we're actually making the drawings and the specifications for contractors to build to. Then we get into construction. That's where we really live. We're ordering materials, fabricating, or manufacturing these parts off-site in a more controlled environment than on-site. And then those things are all shipped to the project site and assembled, I'll call it. Then you're going through a commissioning stage where you're proving that what you built does what you wanted it to do, if I would say it that way. And then you get into operation. What's challenging sometimes with these facilities is they're all the time changing out the tools. And so there's a lot of overlap between design, construct, commission. All those things are happening all the time in various stages of the factory. So it can get quite challenging. Go ahead. So how do you build these things? Like speed to market is probably the most important thing for these customers. As you guys know, the technology is changing all the time. They're now building 2 nanometer process. I think I looked When we went to Masashita in 1998, they were at half micron. So in about 25 years, the chips are about, or the semiconductors are about 250 times smaller than they were 25 years ago. But the way that you can continually evolve these factories is to build them with tons of flexibility. So that's why you see that huge ballroom that Steve showed you, where we can change out tools all the time as new tools are developed that support the new processes. That's how that happens. Just really quick one to talk about the environmental impact. Everybody's concerned about that today for sure. Power consumption is the number one thing for these plants. They use an absolutely extreme amount of power, so that's a challenge. Everyone's trying to go to more renewable resources, wind, solar, water, hydropower. It's very challenging to power these facilities. Data centers are competing for power in a big way. The new AI data centers take just an extreme amount of power. I read the other day that a standard search in ChatGPT takes 10 times more power than a search at Google, just a standard search with Google. So you think about how many times we're using all those things, and nobody's thinking about the power that it takes to feed that. Let's keep rolling. Go ahead.
Could you hit this is actually a video. I don't know if you can hit the thing. So this is talking about a little bit about building safe. So we talk about building environmentally safe, but also we need to talk about building, this is a factory, essentially a chemical factory, right? So how do we build a factory that's safe for employees to work in? And what this is, and I apologize, it's kind of a brief video, but this is actually a catwalk inside of an Intel subfab, which is elevated to about 8 feet in the air. And you can see that everything is kind of caged in. It's probably only 2.5 to 3 feet wide. And there's utilities on each side. So the way that these plants are designed are for easy access. You can see valve handles here. You can see joints and hangers. So everything's easily accessible so that when people are maintaining these plants, they're not straining their bodies. There's ladders that are permanent in place. You don't need to tie off when you go into these places. So it's there's a lot of environmental design that kind of goes into the lifelong aspect of a building, not just how do we get it done as fast as possible.
So when we talk about how much these fabs cost, to build a new factory is somewhere in the neighborhood of $15 to $20 billion for a fab. And so you guys will hear these announcements that have been happening over the last 2 or 3 years where they're building a mega fab, like Columbus, Ohio, Intel's building over there. It's in the papers, you can read about it, but it's going to be $20 billion. What's interesting is about 70% of the cost of a new fab is that equipment, those tools that we talked about. So it's just a massive amount of money spent on these tools. What we do is this process piping right in here. We're like 10, 15% of the overall budget of a new fab. It's still a great business, but obviously the tool manufacturers are the bulk of the cost of building a new fab. And a lot of that is because it's ever evolving, right? And so they're always changing out the tools to keep up with the new process.
Definitely. Yeah, and it's important to know that the tools, these companies may order tools 2-3 years in advance, but the majority of the time that it takes to build one of these facilities is right here, right? Once they figure out what they want it to look like. That's why if you drive past an Intel or a TSMC, every building looks the same. There's a reason for that. It's faster to build it that way, right? And if you go inside of these buildings, I guarantee you, they all pretty much look the same as well.
Even though we can't take pictures of any of them.
Yeah.
Just real quick, and I'm not going to read these to you guys, but you guys are probably thinking, man, I came here to learn about building manufacturing semiconductors. Why are we talking about construction? I would tell you that in all the industries we work in, whether it's refining at ExxonMobil or pharmaceuticals at Eli Lilly, the people that we work for in those companies started out as chemical engineers, started out as mechanical engineers. I'm sure it's going to be the same in this industry. In 10 years, we're going to be working for folks who got into the industry, somehow found a liking or a niche in the construction management and in the process management, and you guys will be running construction projects, believe it or not. Some of you will be inside semiconductor facilities in 10 years. So I think it's great that we're here talking to you guys about what construction looks like. But there are a ton of jobs in the industry, and because of what the industry is doing, just the absolute explosion of the industry in the United States, there's a lot of jobs. You want to touch this one or you want me to?
This just kind of goes into the main thing to take away here. Semiconductor employment has increased 4% year over year. And this is what I think since 2013, and that's from a White House study. And then these are just some of the main skills. You can, as engineers, I think you can all kind of consider. There's just a lot available, and pretty much if you can dream it, you can do it in these industries. You can find a good career, and it's good paying careers. So.
Look at that.
Right on
10
time?
after, baby.
All right.
Well, first, so thank you very much, guys.
Yeah.
Any questions?
Yeah.
Go ahead, right here.
Sorry, you point.
Oh,
We
go
can't
ahead.
both do it.
I was just gonna say, what are some common issues when like constructing the piping systems in semiconductor fabs, and like what do you guys do to prevent these issues from arising?
The biggest issue is everything goes in so fast. You're fighting, kind of trying to work with all the other trades. So we're putting in pipe at the same time the electricians are putting in conduits. At the same time the sheet metal guys are putting in ductwork. Same time the controls guys are putting in wiring. So figuring out where we all need to go, even though we do BIM or 3D modeling of all these sites before we start construction, there's still a lot of coordination that needs to happen in the field to get it done. Yeah. Yeah, go ahead.
could we
Oh.
just get you the microphone?
Oh,
so
sorry.
folks can hear, otherwise they can hear you guys.
Okay, sorry, I didn't know if we were time crunch.
The way you explained about the pedestals that you put, like according to the tools, so there's not only ASML that's working in making the tools. So do you like make the pedestals for each tool separately, or like there is a common thing that just puts in and every tool follows that common?
There is not, well, yes and no. There are every tool from each manufacturer is different. Think of a different model of car from Ford versus Chevy, right? They're kind of the same, but they're different. So same thing with tool manufacturers, especially when you talk about the different types of tools or the different the tools that do different things. They're all going to look different, a little bit different, require a little bit different utilities. So these pedestals, while we may get a contract to manufacture 20 of the same one, we're probably going to get a contract to manufacture 50 different types of pedestals. So yeah,
Pedestals are unique to the
they are pretty
Okay.
unique to the tools. Yeah.
Thank
Yeah.
you.
And what we are seeing more recently is prefabrication. So a warehouse offsite where not only will they build the pedestal, they'll actually have us put the piping on the pedestal before it gets moved into the fab, so that it's already on there. And we don't have to do that in the field. When I talk about field coordination, that helps with that quite a bit. So, yeah. Oh.
So you guys mentioned that.
Yeah.
Okay, you guys mentioned that you use when making piping, it's like really high pure. It's used for like really high purity stuff. Would you guys use like different materials when making piping like that, or is it kind of like just the same stuff you'd find in like a hardware store?
Couple different main ones when we talk clean. Where like the reason I put plastics and stainless up there, those are the two main ones. There's different levels of each one, but when it comes to the two main ones, gases are primarily going to be stainless, or what it's called Hastelloy, which is an alloy. And then for plastics, it's predominantly polypropylene and
Most of it's polypro.
what's the other? Well, PVDF, polyvinyl.
Yeah.
PVDF is the more pure one, is what I would say, and then polypro is a little bit less pure. But those are typically chemicals or waters that can't be transferred. PFA is another one, can't be transferred in metals for whatever reactive reasons. Yeah. Go back there.
I can just yell at that.
It's for the camera.
A pipe was great. That could be pretty like detrimental to the fab. So do you guys have to like quickly go in and fix it?
It happens.
It definitely happens. These plants, as you can imagine, run nonstop, 24/7. They don't take breaks. So yeah, if there's two scenarios I'll talk about. One is a pipe breaks and shuts a tool down, which is pretty detrimental, and Bart will tell you we carry pretty
Hefty
high levels
insurance.
of insurance because that happens. To the extent that a lot of these companies actually self-insure their contractors because they know that this is going to happen. They don't want it to happen, but it's sometimes an inevitability. So they need to cover themselves for that. So yes, we do. We try and go in as soon as we can make it a safe environment for our people to work in. After it's cleaned up, typically these companies will have emergency response team that'll do a cleanup. Then we'll come in, fix the issue, and then to the best we can, and then get it back up and operating.
I will say, though, the plastics that we use for the ultra pure water, in 10 years it gets very brittle, and so you'll have a 3/4 inch valve, doesn't look like much, but it's tied to a main run of piping that's going to shut down tools, and an electrician or a pipe fitter or a scaffold builder hits that valve with his backside, walking through that catwalk, and it breaks off. It happens, and it's a big deal, to your point.
Yeah.
Okay, thank you.
I don't know if you could share with them just an order of magnitude of the kind of money per day that a fab shutdown might consist of. Because I'm not sure, it's hard to grasp quite how much money is involved.
Tens or hundreds of millions of dollars. I mean, a lot of the times it depends on what tools are affected, but yeah, tens of millions of dollars probably minimum per day, sometimes per hour. Yeah. Think about when you think of something that runs 24/7. If you stop for 5 minutes to take a breath, you've delayed that entire factory for 5 minutes. So and when you think about the life of a company or the life of a factory, you've just delayed the life of that factory by 5 minutes. If that happens once a week or once a day for a week, it affects the company quite a bit. So.
And companies like ours won't be in there working for very long
if we keep doing that. Yeah. So.
So how do you come back after a year? Do you come back after a year and check that the piping is still clean? Do you do integrity checks or something like that? How does that work?
Yeah. All of these systems are continuously monitored for cleanliness and purity. So that's an ongoing, everyday monitoring situation.
And talking of purity, I quickly checked. So you're 1,000 out on the human error. It's micrometers, not nanometers.
Is that right?
Oh.
When you guys build clean, again, it's really hard to describe how clean we're actually talking about.
In front of you.
So when you install your piping systems, do you have redundancy built into it, or is it?
Absolutely. So most companies will call it N+1, and you're all engineering students. You're going to learn about this. But if you install a pump, you install a second pump, the same pump, and they're all connected. So if that pump goes down, you switch that to the next one, and then you fix the one that was broken. Or a lot of times they'll just switch back and forth once a week. Run this one for a week, run this one for a week, right? So you're running the same time, and everything's standardized. So if you have to replace one, you got one sitting on the shelf, you just pop it in.
And it's not for just if it goes, it breaks. You have to do maintenance.
Right.
You don't shut the factory down to do maintenance. You switch over to the other pump and you maintain the second one. And so that happens all the time. Good question.
Yeah.
Do you guys have any big competition, and what makes you stand on top against the rest per se?
This is his job. He's a business.
Yes, we have competition. I'd say there's probably 6 big companies around the U.S. that.
Let me say this real quick. And then you
Yeah, go ahead.
So when you're talking about building the building and building the base build of a fab, there's more competition because they trust more contractors to do that. When you get into the distribution piping and the distribution systems, there's kind of another step down of qualifications of contractors that the big boys, the Intels and TSMCs trust to do that work. When you get into the tool install, it's kind of like the highest cover charge and the most qualified folks. We're lucky to be in that world, but there's probably 5 or 6 companies that are doing
Certainly
that.
less than 10.
Yeah.
I mean, when you look at something like this is a gas box, distribution box. These are all valves, but this tubing coming off of it, that's carrying some sort of gas. That's probably an 1/8 inch piece of stainless tube that we have to weld together. Every turn is a fitting that has 2 or 3 welds on it. So, finding people that know how to do that and can do it to the level of cleanliness and the level of quality that's required are few and far between. We kind of pride ourselves in how we set ourselves apart. One is safety. Safety for us and our employees is number one, and we think of that before we do any project. And then 2 is our quality. So we say, you know, you can find 4 or 5 other people that can make those welds, but they're not going to look as good as ours. So that's kind of.
And the other thing that sets contractors apart in this industry and pharmaceutical and refining is when we turn over systems, if they can quickly commission them, you know, without problems and go to production, that's, you know, that's the secret sauce for us. If they've got a lot of problems in commissioning and it takes them longer to get to production, you know, that's a killer for a contractor.
And customer service. I included this because, well, you know Chad. Chad, one of our general foremen built this for a customer. It was a totally custom solution to something that somebody he knew at the factory said, hey, can you build this for me because I think it'll work and blah, blah, blah. Anyway, we ended up coming up for it. And you can see, I mean, there's some welds that, you know, it's probably not the prettiest thing in the world, but it probably helped our customer out. So custom solutions like that and customer service is a big part of it as well.
So I was going to say, if we can give them a final round of applause. Now, hopefully you guys...